So let's go on where we left off in part one. This is part two of the RSA algorithm. So we talked about the modulus before and gave an example of it on the 12-hour clock. Now we're going to show how we actually can use the modulus. So start here. I'll say first you choose two prime numbers, p and q. That's what's usually used. Then you compute n equals p times q. Next, form the factored function, and this is where it takes a little explaining. F of x is actually a factored case of p minus 1 times q minus 1. It's not so hard. It's That would be something that most people learn in second semester algebra in high school. So far it's quite simple. Next, things get a little more complex. Now we have to choose an exponent e such that the following is true. 1 is less than e, and e is less than the greatest common denominator. Hereafter I'll refer to that as GCD. And e, comma, p minus 1 all equals 1. So that's actually an inequality there that we're looking at. And 1 is less than e less than GCD for e comma q minus 1. In other words, the two different factors of this equation above must both be within this interval range that we're talking about. So to go on, actually the inequality is 1 less than e less than GCD of the function f of x equal 1. But this means it has to be true for each factored term of f of x. This means that e, p minus 1, and q minus 1 have to have only one common denominator, and that is 1. It's not important to know why p and q must have only one common denominator to use RSA. It involves certain aspects of algebraic sets, which I won't discuss here, perhaps in another video. Just know that they have to have this property. What this means is that the two numbers p and q are coprime. That is, they have no factor between them except 1. There is a way to determine if the two numbers have only 1 as a common denominator, and it's called Euclid's algorithm. You take the two prime numbers and divide them repeatedly until you get down to 1 as the remainder. If you don't get 1 as the remainder in this process, then the two primes don't have 1 as their GCD. Here's an example with a table that shows how it works. On the top, we have the dividend, the number to be divided, the divisor, the quotient, and the remainder. We divide the two numbers across and move the divisor to the second row and repeat the process until we get 1 in a row. If we get 1, then the two numbers have only 1 as their GCD. We will use 140 and 21. So let's take a look at the Euclid algorithm table here. And you can see it right there. Now we'll go through it below. In the first row, we have 140 divided by 21, which equals 6, without the remainder. 6 times 21 is equal to 126 minus 14, or just the reverse. 14 is the remainder. Moving the 21 from the first row down to the second row, we have 21 divided by 6, which equals 3, without the remainder. 3 times 6 is 18, minus 21, the remainder is 3. We move the 6 down to the third row. We have 6 divided by 3, which equals 2, and 0 is the remainder. So now we repeat again, and finally we get 1 as the remainder. In other words, 3 divided by 2 leaves you with 1. And this means that 140 and 21 have one GCD equal to 1, which is exactly what we wanted. Okay, so now we finally come to the payoff here, and I'm going to give a numerical example of the RSA algorithm. But we'll do that in the next video.